Okay, so what I'd like to take a look at now is trying to make some connections between the idea that we had of confidence intervals back in chapter 8 and then trying to look at hypothesis testing that we're taking a look at number in chapter 9. So just a few things here. So let's try to connect the dots here. So one major thing that we should know is that they're both inferential statistics. Remember, we had descriptive statistics and we had inferential statistics. Descriptive statistics, that was just simply taking what data we could have, we could collect it, we could summarize it, we could just do some computations with it, that's fine. But the key difference between that and inferential statistics is that in inferential statistics, we're going to take something from a sample and then generalize it to a population. So in both instances, we're taking information about a sample and trying to look at something about a larger population. Okay, great. So that's one major connection between those two. The other one is that they both use distributions and or the central limit theorem. And that's what I like to focus on today, is this idea of how do they both kind of tie into the same statistical background and I guess kind of foundation behind how we can do any of these meaningful computations. All right, so a few things I want us to recall is if we look at means with known population standard deviation. So if we look at enough of these samples, we form a normal distribution. This was the central limit theorem for means. It was really great. This is what it looks like, is that the sample mean, this distribution of means, is approximately normally distributed where this is our mean and this is our standard deviation. Okay, central limit theorem for means, that is what we were using back in chapter 7. This is going to be behind the scenes of both the confidence intervals when we have known population standard deviation and we're looking at means, and it's also behind the scenes for hypothesis testing for means when we have a known population standard deviation. So this is the distribution underlying both of them. Same thing up here. If we're looking for means but we don't know the population standard deviation, we said we don't have a normal distribution, but we have a student t distribution. This requires this distribution where t sub degrees of freedom. Remember, the degrees of freedom is just n minus 1. So again, in both confidence intervals and in hypothesis testing, if you're looking at means with an unknown population standard deviation, you have to be using this distribution at t sub degrees of freedom. And then also for populations, when we have the populations form a normal distribution, and then this was our normal distribution, in which case we normally substitute in p prime, q prime, and n because we don't normally know what p is. But again, this is going to be behind the scenes in both confidence intervals for proportions as well as hypothesis testing for proportions. So when it comes to the homework questions, you're going to have some homework questions that are going to be very similar to the ones you had back in confidence intervals, in which you have to find the type of distribution it is, maybe even what type of variable we're assuming, right? So if we're looking at sample means, it will tell us, okay, we're looking at means. And so in all of the questions that you might be seeing related to this, treat it the same exact way as you did with confidence intervals. It's going to have the same type of distribution that's underlying all of the math. So what I'd like us to now start to see is compare the two. So remember, we drew this picture a lot with confidence intervals, and maybe that made a lot of sense of we had our sample mean here, and then we said, okay, about 95%, for instance, we could say 95% of our data is going to fall between these two values. We could find what these two numbers would be, and so the first day that I described confidence intervals, I went through the math of how did we use the central limit theorem, how did we use all of this to come up with these numbers, and we said, for instance, for 95% confidence intervals, this had a z sub alpha divided by 2 of 1.96, and then we multiplied it by things, and we added it or subtracted it from our sample mean. Okay, so our confidence intervals, we had our sample mean was going to be in the middle. Then Remember, we said confidence intervals, they said it may or may not contain the population parameter. So this population parameter, it's going to be somewhere. I'm not quite sure. Maybe it's chilling inside here, so maybe over here is where our mu value would be. So maybe mu is, I don't know, 40, this is 30, and this is 45. Mu is going to fall within that range. Okay. But there's also the possibility that our population mean might be outside of this confidence interval. That's why we only have a certain degree of confidence. We can never be 100% confident, but we could be, say, 99% confident. But there's still the possibility that our population parameter falls outside of the range of this. Now, if we move on to hypothesis testing, what's taking place is we have this mean in the middle. Our population mean mu is going to be this middle value taking place. This is our null hypothesis. Everything is based off of our null hypothesis saying, what if nothing's different? Then our sample mean is going to fall someplace else, right? So we take our sample and we're going to say maybe it lands over here as our x bar. Obviously, we know that things are different. The question is, how significant of a difference is there? So we saw, for instance, we looked a little bit at p-values, and so we said p-values, that's the probability that we're going to be as extreme or more extreme if we take another sample. So again, there's areas associated with this, so the p-value is going to be something out here. So remember, a very tiny p-value means that we're going to be way out here. We're going to be really far away from this mean, and we're saying that's surprising, so something's probably different about that group. So in this case, in confidence intervals, our sample mean's in the middle. In this case, our population mean is in the middle for hypothesis testing. So if, for instance, I have, say, my sample mean occurs here, I could really draw the same type of distribution taking place at this point here. So you could draw both of these distributions on the same line, or on the same, line, you would say. So in this case, notice that now when these two are very close to each other, then in this case, if we think about this one just kind of being brought down here, if we're really close to each other, well, in this graph, the population mean is going to be close to this, and in this case, the sample is going to be close to this. So our population mean will fall within the range of our confidence interval, and we're going to get a very large p-value, so we will not reject the null hypothesis. We're going to say that we're just going to chalk that up to random chance. We're thinking that that's nothing special. But if this is really, really far away, so let's say this point is even further this way, and so this distance is far away, well then we're going to be rejecting the null hypothesis because this is going to have a very small p-value if this is very far away. But by the same note up here, that if the distance between these is really big, then that means that, say, our population mean is going to be way out over here. And then we're going to say, wait, the population mean doesn't fall within our confidence interval anymore. So that leads us to this result that ties the two of these together. So if we do a two-tailed hypothesis test, a two-tailed test, that means that we have both values on the left and on the right. So we're saying if you're as extreme or more extreme, you're going to be either really larger or very small. So two-tailed hypothesis test, the alternative hypothesis has not equals. So you can be either larger or smaller. Okay, so for this, we're going to reject the null hypothesis at a level of significance of alpha. So our alpha, that's going to be assigned to us. Maybe that's going to be 0.05, for instance. If and only if 1 minus alpha, so if alpha was 0.05, 1 minus that is 0.95. So as a percent, that's 95%. So if alpha equals 0.05, then we're looking at a 95% confidence interval. So if we reject the null hypothesis at alpha equals 0.05, the 95% confidence interval will not contain the hypothesized population parameter. Vice versa then, if we do not reject the null hypothesis, so if we're saying that there isn't much of a difference, well then the confidence interval will contain the hypothesized population parameter. So kind of what I visualized here about if these two are really close, then indeed we're not going to be rejecting the null hypothesis, and this population parameter is going to be within the confidence interval that's related to each other at this level of significance as well as that given confidence interval. So that percent that appears is indeed the same with both of these. So technically, doing one of them is somewhat doing the other one, except it's just giving you slightly different information. The confidence interval gives you a range of values, as opposed to hypothesis testing has some type of definitive claim at the end of whether or not we do reject the null hypothesis. So hopefully that maybe helps bridge a little bit of understanding between these two areas, is that they're not completely distinct. They are going to be somewhat similar. We saw the similar undertones of the distributions. You're going to have similar undertones of these alpha values, and there's going to be similar undertones of looking at these types of pictures on your homework as well. So if you have questions on any of this, please don't hesitate to ask, because this is some very big picture understanding to try to see how are these two interrelated.